Hey, how's it going? This is lecture 6A for Engineering 270. This lecture replaces the previous version of 6A, which was made in the heat of summer a number of years ago, and I had the air conditioning blasting, and you couldn't hear it. So the next video will talk about the poor audio quality of 6A. That doesn't apply anymore because we got a new lecture here. So this is a lecture on stacks. Stacks are a fundamental concept in computer science, in other aspects of engineering, and in fact in daily life. We sort of deal with stacks. If anybody out there plays Magic the Gathering, there's a stack that you have when you have multiple people putting down effects. They go in a stack and they get played in a certain order. It's a concept that pops up a lot. And in this course, since we're working with assembly language and we're working with a microprocessor, we're going to look at how a stack is implemented at a very low level. But everything we talk about here will pretty much apply to how stacks are used at a higher level. And if you're doing the computer science sequence, when we get to CSE 222, which is our first data structures course, we'll revisit stacks, but we'll look at them from a higher level perspective. But you'll see some of the things that we're doing here popping up then. So let's talk about a high level setting where stacks occur, and this is in the notion of calling functions. So if you think back to like CSE 121, we might have a main program, and our main program might do a number of steps, and at some point we want to, we want to print something, and so we basically make a call to a function called printf. Now we don't say call printf, we just say printf, but it means, hey, I want to stop what I'm doing in my main program and I want to find some other set of code called printf, which takes my arguments and converts them into ASCII characters and sends a bunch of output to our display. And then at some point when printf is finished, I want to come back here and I want to continue with my main program. So, this is stored somewhere in memory, our main program, and printf, because our main program needs it, when we start to execute this code corresponding to printf, is also stored somewhere in memory. And so, we know about goto statements. We can take our main program and we can say, hey, at this point, jump over here and start executing. And then when we get to the end, come back here. So there's two problems with that. The first problem is when we get to the end of printf, how is it going to know that it should come back to this statement? Because this code is kind of fixed, right? That's not code that we're writing. That's code that's provided for us. So we would need some way to tell it, hey, when you are done and you're ready to leave printf, come back right here. The bigger problem is in our main program, we might make multiple calls to printf. And so after this call to printf, when we're finished, we want to go back right here. But after this later call to printf, when printf is finished, we want to go back right here. So we can't just have this thing jump to a fixed location. It's got to be told where it should return to when it's finished. Now, we could go ahead and just, say, hey, I'm going to take this address, the location of this instruction, and store it somewhere. I'll store it at some magic location, 17, and printf will always look in location 17 to see where it should return to. So before this call to printf, I'll store this in our magic location. Printf will read that and say, oh, I should come back here. And on this call, I would store this in our location, and printf would say, oh, I should return here. And that almost works, except that we can have nested calls. So inside my main, I might call some function fun1, and fun1 might do some stuff and call printf. Let me say call here, even though we don't say call, right? So when I make this call to my function 1, I would want to store this location somewhere so that when fun1 returns, it can come back here. But inside fun1, I'm going to have to do the same thing. I'm going to make a call to printf. I'm going to need to store this location somewhere. So that when printf gets to the end, it can say, oh, I should come back here. And then when fun1 gets to the end, it will say, I'm going to come back here. So we need to be able to store these locations to which we should return, and we need to be able to store more than one of those. Alright, so how do we do that? Well, we use a data structure. And it's a data structure which is characterized as being last in, first out. And this is something called a stack. And the idea of the stack is when I make my call to fun1, I'm going to take this location, let's call this location A, and I'm going to save it somewhere. So here's my stack. And I'm going to save A there, and my end of my function will look at what I put on the stack and jump back there. So I'm inside fun1, I'm going to make a call to printf, and let's say this location is B. It's also going to save B on the stack, but it's going to save it on top of A. So that when printf gets to its end and it's ready to return, it will look at what's at the top of the stack and say, oh, that's a B, I'm going to return to location B. And it removes that from the stack. And then when fun1 gets to its end, and it says, hey, I need to go back somewhere, where should I go? It'll look at the top of the stack, say, oh, I should go back to location A. It'll go right here, take that off the stack. So this idea of a LIFO, last in, first out, is a structure where we can continually store multiple things, and we can get the things back that we've stored there in the reverse order that we stored them. And the reverse order is the right thing to do, because if I make a bunch of function calls, I might call 18 functions. That 18th function, when it says return, it should return to the last thing that I stored, that 18th thing that I stored. So we want this last in, first out structure. So here's a physical example of a stack. I have an empty stack, that's this piece of paper. I'm going to make a stack of books. So I'm going to put down a book on hacking. That's the thing that's on the top of the stack. And now I'm going to put down a book of coding haikus. And that's the thing on top of the stack. Now if I come along at some point and I say, what's on top of the stack? It's not the book on hacking. It's this book on coding haikus. That's the thing that I just put on the stack. And this thing that's underneath it is right now not accessible. The only thing I can take off the stack is the thing that's on top. Once I take that off, then I can get to this thing that I put on earlier. So let's suppose I got my book of haikus. And now I've got a mysterious black book, which is a book of what's called Medusa circuitry. So that's sitting on top of the stack. And now I've got a book of chess exercises. So if I come along and I say, what's on top of the stack? It's the chess exercises. Is there a book on hacking? Is there a book of haikus? Yes, but they're not available yet. But at any time I can say, give me what's on the top of the stack. If I say that right now, I get the book of chess exercises, and now the black book is on the top of the stack. And now if I want to put something else on the stack, like a book of essays by Sartre, that goes on top of the stack, and that's the only thing that's accessible. And I can't get to the book of haikus or the black book or the book of hacking. But I can say, hey, let's take the top of the stack off. That gives me this book. Now the black book's accessible. I can take that off. Now the book of haikus is accessible. And maybe now I want to put the book of chess exercises back on the stack. Right? This is a physical representation of what's going to happen in software or inside the hardware of the PIC processor. So we should really be thinking of this pretty literally as a stack of things to which we can add to the top, from which we can take from the top, and in general we don't monkey with anything below the top of the stack. Alright, and there's two particular edge cases that we should know about. The first edge case is if I keep putting things on the stack, so I'll add a remote control and I'll add a pen. And if our stack gets too high, we'll find that it can't hold anything else. If we try to put something else on top, maybe it falls over, or maybe it has hit the ceiling and there's nowhere left to put anything on top. So that's called a stack overflow. when your stack is completely full and you try to put something else in. So imagine that you're stacking inside a bookshelf. You can only stack your books so high, and then you're hitting the top shelf. Now if you try to put something else on top, there's nowhere to put it. That's called a stack overflow. The other situation that can occur is you keep removing from the top of the stack. And right now there's one thing on the stack, it's the Book of Hacking, and I remove that. And now I try to remove from the stack, but the stack is empty. So that's called a stack underflow. And so these are two conditions that can pop up: an overflow, which is when you try to push when full, and an underflow, which is when you try to pop or remove from the stack when it's empty. So those are possible error conditions. So let's detail these words, push and pop. Push means add to top of the stack, and pop means remove from top of the stack. And those are mostly the two things we do with stacks. We push and we pop. Push is adding, popping is removing. Alright, so how can we make a stack work in software? Well, think about an array. So imagine that we have an array. Let me call it stack. And let's say our stack has 8 locations in it. So let me label the indexes here. So there's an array of 8 locations. And the idea is when we want to push something onto the stack, we're just going to store it in one of these 8 locations. Now, which location are we going to store it in? Well, we could use any location we want, as long as we have a way of knowing where we stored the last thing, so that when we say pop, we can get back the last thing. So we're going to use something called a stack pointer. You'll often see this just written as SP, but on the PIC processor, it's actually called STKPTR. So we can use any of these names. And we're going to initialize our stack pointer to 0. And so if I say let's push, I don't know, let's push a Book of Hacking, here's what's going to happen. We could take that thing and we could store it in this array element specified by SP. So we store it at location 0, and then we increment SP. And now if I want to push a book of poems, where do I store that? Well, I look at SP. SP is equal to 1. I store my poems right here. And then I increment my stack pointer. Now I want to push a book of chess moves. Well, I look at my stack pointer, it's equal to 2. I store my chess book right here at location 2, and I increment the stack pointer. Now if I say pop, how do I find the last thing I pushed? Well, I look at my stack pointer, it's a 3. I decrement it to a 2, and I say, hey, what's at location 2? Book of chess moves, that's what I pop off the stack. If I say pop again, I take the stack pointer, subtract 1, go to my stack, look at what's stored at location 1. It's a book of poems. That's what I pop off my stack. If I try to push something else now, if I say let's push Book of Essays by Sartre, where do I put it? Well, I look at my stack pointer. My stack pointer is a 1. I store this at location 1. And I increment my stack pointer. So by using an array and a pointer, a variable that gives me an index into this array, I can implement a stack in software that mimics this physical stack of, say, stacked books. And a couple of things to note here. The first thing is, when I popped off my book of chess moves, I didn't actually remove it from memory, did I? It's still sitting in this array, but what I did was I subtracted 1 from the stack pointer so that the next time I said pop, it gave me this book of poems. Because it no longer saw this as part of the stack, but it was still sitting in memory. If this was actually an array of books or numbers or strings or something, whatever I copied into here when I said push is still sitting in there. And that's a good thing to know and think about from a security perspective. When you pop from a stack, you don't necessarily remove it from memory. Now you can modify your pop so that it overwrites it with some value, or you can change your hardware so that when you pop from a stack it gets overwritten with garbage, but by itself, just a pure abstract stack, popping doesn't actually remove it from memory. It simply changes the stack pointer to say, hey, this is not considered part of the stack. So if you want to store something else there, you can do so. Okay, and of course if we do one more pop, we'll subtract 1 from the stack pointer, we'll return sart. If we do another pop, we'll subtract 1 from the stack pointer, it becomes a 0, we remove the book of hacking. If I were to say pop again, and I were to decrement the stack pointer, my index would become -1, and there is no index -1 in this array. That's how I know I get an underflow. On the other hand, if I've pushed all the way up and my stack pointer points beyond the top of my stack, and I try to push, that's going to give me an overflow. Alright, the other thing I want to point out is that the way we're implementing this is as follows. Push. So to do our push, we're saying copy to stack pointer, and then increment the stack pointer. And to pop, we're saying decrement the stack pointer, and then copy from stack bracket SP. But that's only one possibility. There are other ways that we can implement a push and a pop that work perfectly well. For example, we could increment before we copy, and we could decrement after we copy from a pop. Or we could choose to start the stack up here and decrement when we push and increment when we pop. So there's multiple ways to do this. This is, I think, the most natural way, the easiest way to talk about, but it's not exactly what happens inside the PIC processor. The PIC processor does something a little bit different. When you say push, it first increments the stack pointer, and then it copies to stack SP. And when you say pop, it copies from stack SP, and then it decrements the stack pointer. So we say push is a pre-increment, pop is a post-decrement. And on the PIC, so this is on the PIC processor, the stack actually has 32 locations. And the stack pointer is initialized to 0. But notice what this means. When I first push onto an empty stack, I'm going to increment the stack pointer to 1. I'm going to store right here. So this index 1, that's where the first thing gets pushed on the stack. So location 0 never gets used. And in fact, doesn't exist physically in the chip. So that decision was made by the designers of the chip because, you know, a million factors that came out to be the best decision. Alright, so 32 elements in the stack. The first element 0 is not actually available, so we have 31 things that we can store in the stack. Stack pointer tells us where the last thing is that we pushed. So if I were to push something onto the stack, it would increment the stack pointer to a 1, and it would store whatever I pushed right here. So at any time, stack pointer tells me the last thing that I pushed. And then if I say pop, it would copy the thing at location 1, decrement the stack pointer to 0. Alright, the other concept we want to know is the top of stack, which is called TOS. And TOS is simply the value at the top of the stack, the value of the thing that we pushed last. So if I push something onto the stack, I increment a stack pointer to 1, and let's say I push the number 173, top of stack would contain the value 173. It's the contents of the stack at whatever the stack pointer value is. So we can look at top of stack, see what's sitting on the top of the stack, and then we can pop to actually remove it. Alright, so let's dig a little deeper into how this works on the PIC processor. So when you say call some location, what does it do? Well, it basically pushes the address of the next instruction onto the stack. So let's say I'm at location, let's say I'm at location 32. And at location 32 there's an instruction which says call some location. And maybe that location is, 88. Alright, the processor needs to remember where I should jump to when I'm done executing this code down here at this location. So it finds the address of the next instruction. Now call takes 4 bytes, so the next instruction is going to be at location 36. So it's going to push 36 onto the stack. So whatever our stack looks like, wherever the stack pointer is pointing, 36 is going to get pushed on there. And then it's going to go to location, which in this case is 88. So somewhere at location 88 there's some instructions happening. At some point we're going to hit a return instruction. What is return to? Return says pop top of stack, and then go to that location. So if nothing else has happened with the stack in here, when I get to a return, it's going to look at the top of the stack, see there's a 36 there, pop it off, and then it's going to go to location 36, which brings it up here right after the call instruction. And this happens for you automatically. So you can use call and return just like we call functions and return from functions in C. But we need to understand how this is happening. And the way it's happening is when we say call, the address of the next instruction is pushed on the stack. When we say return, the return address is popped from the stack. So if inside here, before I say return, I make another call, the address after that call would get pushed on the stack up here. And when that other function returns, it'll pop off that address, continue, and eventually I'll get to this return, pop off the 36, go back to the instruction after that first call. So mostly we interact with the stack by saying call and return. But there's one other pair of instructions we can use. We can also use the instruction push. And push simply takes the address of the next instruction, pushes it onto the stack, but it doesn't actually do a call. And pop simply decrements the stack pointer, but it doesn't do anything with the value that it popped. So push and pop we don't use that much. Mainly we're just going to use call and return. Call saves the next address on the stack. Return jumps back to that last address. Alright, and the last detail to talk about here is how these are implemented inside the PIC processor. Stack pointer is a special function register. It's 8 bits, like all SFRs. But it has to store a value from 0 to 31, which only takes 5 bits. So what does it do with those extra 3 bits? Remember, with a PIC processor and most other reduced instruction set machines, memory is precious, right? So the goal is not to waste memory. So let's take a look at the data sheet. And let's look at the stack pointer. So it's a special function register. And it's got 5 bits that are initialized to 0, and then an unused bit, and then 2 extra bits. So let's see what the stack pointer actually looks like. So the low 5 bits, those are the actual stack pointer. Bits 4 through 0, those are the 5 bits that make up our 5-bit number from 0 to 31. This 6th bit is unused. This next bit is the underflow bit. If this bit is a 1, it means we had a stack underflow. And the last bit is the stack overflow. And if this is a 1, it means the stack overflowed. Alright, so that's the stack pointer register. And then top of stack shows us the value that's actually stored at the top of the stack. Well, you know, we said our stack in the PIC processor is 32 elements. But we don't store books, we don't store strings, we store numbers. But they're very long numbers. They're numbers that are approximately 21 bits wide. These are memory locations. Now we know on the PIC processor we can have 1,000 instructions. That takes 10 or 11 bits to store. So storing 8 bits wide is not enough to store a return address. So the stack is actually 32 elements long, and each location is about 21 bits wide. Well, the top of the stack, you know, that's a special function register, but special function registers only store 8 bits. So how does this work? Well, it turns out we use 3 special function registers, TOS L, H, and U. And TOS L, that's the lower 8 bits of the stack register. TOS H, that's the next 8 bits of the stack register. And TOS U, that's the upper 4 bits of the stack register. So we've got 8, 16, a total of 20 bits. And if you want to see the full 20-bit value that's stored at the top of the stack, you take these 8 bits, and then immediately to the left of that you write these 8 bits, and immediately to the left of that you write these 8 bits. And that gives you the 20-bit value that's stored on the stack. So this is something we'll see more when we deal with timers and when we deal with some other subsystems. This idea that sometimes these special function registers, because they can only hold 8 bits, don't hold enough information for what it is we want to store. We need to use 2 or more of these registers in tandem to represent a number bigger than 8 bits. And this is an example of that. If we want to know what's on the top of the stack, we can look at those 3 TOS registers and put them together to actually get in this case, a 20-bit number. So the data sheet, as always, talks about all of this stuff in great detail. If you look at section 5.2, return address stack, it's got some good pictures. Here's a picture of what the stack looks like. Location 0 doesn't exist, so the first thing that's pushed is stored in location 1. The last address available is location 31. That's 11111 in binary. And if the stack pointer has this value right now, which is the value 2, TOS refers to what's stored in memory at location 2, which is this number 1A3H. So the top of stack upper is 0, high is 1A, lower is 3H. 0, 0, 1A, 3H, that's the value at the top of the stack. So that's basically all there is to the stack. A lot more complex to talk about than to actually work with or probably understand. That's a lot of detail I've given you, but that's basically everything there is to know about the stack, stacks in general, stack pointers, error conditions, overflow, underflow, how we use the stack, call and return, as well as occasionally push and pop, and the implementation of it in terms of special function registers. Stack pointer is a 5-bit register with 2 flags tacked onto the end, and top of stack is a set of 3 registers that let us see the actual 20 or 21-bit value stored in the stack. The reason I say 20 or 21 is because on our processor there's only 1,000 instructions, which we can represent with 10 bits, but each instruction takes 2 bytes. So we actually have 2,000 bytes of memory, even though we only have 1,000 instructions. So depending on whether you're talking about individual locations or individual instructions, there's a potential difference of 1 bit one way or the other. And I don't want to get bogged down in that, so 20 or 21 bits wide. Alright, that's the lowdown on stacks. Alright, thanks.